Hi, I'm Jordan.
And I'm Josh.
And we're the AstanzaLaser Science Guys. And today we're going to be teaching you a little bit about how lasers and light work and interact with each other. Hey Josh, did you know that laser was an acronym?
I didn't until I got here.
Well, you're going to learn more about it today.
And so will you.
So the first letter of the acronym is L, which obviously stands for light. Now, light is just part of the electromagnetic spectrum. It goes all the way from radio waves, which gives you music in your car, and then all the way to gamma radiation, which you get from the birth of a star or the Incredible Hulk. So our lasers are somewhere in between those two, mostly using visible light to do the treatments onto your skin.
Yeah. We have a great way to show you the difference between kind of polychromatic light and filter light, which is still polychromatic, right? You can still have a couple different variations of green or blue or red in a narrower bandwidth. We're not quite at one wavelength monochromatic light like a laser, but we're getting there. We have our flashlight here, and you can see here that it's white light and it's polychromatic. So that means it has all the wavelengths of light that we can see with our eyes all in one, which is why it appears white to us.
Now, we're going to put a filter in front of our flashlight and filter out the light so we can get that narrow band that Josh was talking about. Lights, please. As you see, when we apply the filter, our white polychromatic light turns into just a couple shades of red. Now, let's try it with green. You can see now it's just green filtered light.
Great. Lights on, please. Awesome. So when we talk about laser light energy, we're talking about one very specific wavelength, like 1064, 532, 694, 755. And those pieces of light have one other piece that we haven't talked about yet, and that is a vector, right? When we shine a flashlight into the room, it comes down in a cone, bounces off of everything, and we can see very, very well or a little bit better in the dark, right? You got to find your keys, power goes out, etc. Now, when we talk about a laser, that has enough energy that it's going to be directionally focused. And directionally focused means when it starts, it's going to have the same shape and size, if it has no lens in front of it, from one place to another. And for that, to the lab.
To the lab.
Thanks, Josh and Jordan. My name is Nick the Quick, and this is the Astanza Lab. So right here, we got the duality, the Astanza duality to be more specific, and it's responsible for producing two wavelengths. You have 1064 nanometer and 532 nanometer. Now, 1064 nanometer is an infrared light, so it's not on the visible spectrum. This is exactly why it is good for targeting those blacks, grays, all of those darker pigmented colors, or darker tone colors, in other words. And 532 nanometers is good for is a green light, so it's good for targeting those reds, pinks, oranges, all of those warmer tone colors. Now, Josh and Jordan were telling y'all about polychromatic light, and they got a flashlight to illustrate that. However, here in the Astanza Lab, that is not the main type of light we are worried about. The type of light we are worried about is monochromatic light, meaning that it is just one color. So for instance, 1064 is an infrared light. So it's not on the visible spectrum, which is exactly why it is good for targeting those blacks, grays, and darker tone colors. Now 532 is a green light, so it's good for targeting those red, pinks, and all those warmer colors. So another characteristic of a laser is that it has to be collimated, which means it keeps a structural integrity throughout space. So no matter how far I shine it, it won't get bigger, it won't get smaller, it will stay the exact same. So here we have our aiming beam right here, and all that is just the pilot light showing where the laser will fire. You see it on my hand, and you see it against the wall. Now this light does not get bigger, it does not get smaller, it is collimated, which is why it's also a laser. Wait, we can't forget the proper eyewear. As I said before, 1064 is good for treating those blacks, grays, and darker pigmented colors. And the magazine paper is going to react similarly to the way your skin reacts when the pigment is targeted and the pigment, it just kind of is released in your body, and this, you'll see it in the magazine. So you hear that loud snap. That is exactly what we're looking for, and that is indicative of a proper treatment. Now, the cool part is when I treat area without color, without pigment, the snap isn't as loud, and that's because the laser is not reacting with the pigment because there is none to react with. This means that lasers are completely and 100% safe if used properly and you have the proper eyewear. Join us next time to see the laser fired on the actual real-life Homo sapien. Wow, so cool. I'm excited. Anyways, thank you for your time, and back to J-Dub and J-Bird in the classroom. Until next time.
Now that we're done with the lab, let's move on to A, right? A stands for amplification. So first we have light, and now we have to amplify that light in order so that we can do treatments with it. How do we amplify that? By the next letter, S, which stands for stimulation. We have to add energy into our system, whether that be with just voltage, right? In a diode laser, or a flash lamp in a solid state laser. A flash lamp is just a very bright light, right? We use those mechanisms to add energy into our system so we can amplify the light, so we can do our treatments.
Okay, now that we had talked about the A and the S in laser, here's a little graphic to show you. As you can see, as you drop the ball in, it excites the other balls on the mousetrap, and then we get this big, crazy explosion, this big buildup of energy, right? Kind of watch it again. One ball goes in, it excites the rest of them. This is the stimulation portion of amplification. So we stimulate it by dropping the ball in, and then it's amplified by the rest of the mousetrap balls, right, to continue to propagate that until the entire area is excited. So what do you do now with all of this energy that you just built up? Well, if you've ever had a bunch of kindergartners that you've just given a bunch of candy and sweets to, there's really only one solution. You got to open the door, you got to direct them out to go play. And that brings us to E, emission.
As Josh said, we got all this energy in our room full of kindergartners, right? And now they're hyped. There's too much energy in the room. It's unstable, right? We can't live like this. So we need to get these kindergartners out of the room. Similarly in our laser, we have the exact same situation going. We've done our amplification, we've done our stimulation. Now there's too hype in this laser, right? So as the kindergartners leave the room, as the energy comes out of the system, it gets emitted as a particle of light called a photon.
And when we talk about the photons in the laser, right, we're talking about how do we gather them up to put them on the playground, right? That's the big question, right? Because they're gonna go everywhere. So think about it as kind of shaking up a bottle of champagne. It's the way I like to think about it. You have a cork, which you can pull out, and you have the glass end, which for all intents and purposes is not breaking, right? Unless you drop it or whatever. But for this model, it's a perfect seal for the champagne. And we are shaking up the champagne, shaking up the champagne, shaking up the champagne. At some point in time, we are gonna bounce the champagne around, like the photons, in the laser for the light cavity, and eventually one of those sides, the cork side, is gonna pop, right? And we're gonna get all of that energy out at once, right? That's a little bit different for a couple different variations of lasers, but for the propagation and amplification and emission of radiation, that is how it works. So once we get all of that shaken up, we have our photons gathered up, we got them all together, we push them all out the door at once in our photon kindergarten class, and that is going to produce our beam of light, right? And those photons and our kindergartners are bouncing up and down at a single wavelength of light, 1064, 532, 755, 694, right? That is where we get our monochromatic light and how we get the energy to do work from the laser.
Now finally, we're on the last letter R, which stands for radiation. Now those photons that Josh was talking about are technically considered radiation, but like I said, light, a lot of things are considered radiation. Light is part of the electromagnetic spectrum. The electromagnetic spectrum includes everything from radio waves all the way up to gamma radiation. Now how do we differentiate between good radiation that we can use for lasers and bad radiation that can harm you, right? Well, we differentiate those between ionizing and non-ionizing. ionizing radiation is really powerful, has a lot of energy, and that energy can hit your DNA and change it, causing cancer. Non-ionizing radiation is what you encounter every day, right? Radio waves, even your microwave is non-ionizing radiation. Those are just going to pass right past your DNA and not even mess with them or change them at all. Right? So our lasers use very good non-ionizing radiation, can't harm you, can't give you cancer, which is kind of what we like.
But just as looking at the sun hurts your eyes, so can lasers. Always wear your goggles.
Absolutely.
Now that we've walked you through the acronym of LASER, light amplification by stimulated emission of radiation, I hope you learned something great. I hope that your laser knowledge is a little bit stronger than it was the day before. If you have any questions about that, please comment and we'll get back to you and answer any relevant questions that we can. And from all of us here at AstanzaLaser and the Science Guys, I'm Josh Walsh.
I'm Jordan Hall.
And we'll see you next time.